Tonight's presentation is titled GA and Big Data. It's part one of a two-part series. And our presenter is Mike Busch. Mike is president of Savvy Aircraft Maintenance Management. He's author for numerous aviation publications. He has a certified flight instructor certificate, an A&P mechanic certificate with the inspection authorization. In 2008, FAA's Aviation Maintenance Technician of the Year. And Mike is a member of EAA. Mike, thank you so much for volunteering your time and being with us tonight and sharing this information. I'm going to turn control of the presentation over to you.
Okay, well, good evening, everybody. Good evening, Tim. Tonight's presentation is going to be a little different than the sort of thing I usually do. And as Tim mentioned, it's the first of a two-parter. I'll be doing the second half of it next month. And the subject is general aviation and big data. And I want to talk to you about some of the things that we are learning and able to do with a large database of real-time flight data that we have been gathering over the past 4 years from general aviation airplanes. We have a database of about 1.2 million flights now from about 9,000 different aircraft, and that's enough data to do some really interesting stuff. So I'm going to be talking to you about some of the stuff we've been doing with this data tonight and next month when we do the part two of this series. The first thing I want to talk to you about is it's kind of more fun than anything else. It has to do with the subject of headwinds versus tailwinds. There was an editorial in Flying Magazine back in the 60s that was written by the then editor-in-chief of Flying Magazine, Bob Blodgett, who passed away. Who's long since left us, and he wrote something that I think most aviators have thought from one time to another. And what he said in the magazine was, we all come to the conclusion that there are always more headwinds than tailwinds, and that the headwinds are always stronger than reported or forecast, and the tailwinds are always weaker. And now Blodgett wrote these words in '68. And died in 1973, and back when he was alive, this was the sort of thing we could really only speculate about. But in today's era of digital avionics and big data, where we are able to collect information on millions of actual real-world flights, we can actually crunch the data and prove these things and actually determine their magnitude. As I mentioned, over the past 4 years, the SavvyAnalysis division of my company has been building a database of digital engine monitor data, and we now have about 1.2 million flights flown by nearly 9,000 different piston-powered GA airplanes of all kinds. Ranging from tons of RVs and other experimentals up through a big cabin class piston twins, and we gathered this data by having aircraft that were equipped with digital engine monitors dump the data and upload it to our system, and they do that so that either they or we can analyze their data and help troubleshoot their engines and so on. But as a byproduct of that, we've been able to accumulate this very large amount of data. And when I say a large amount of data, typical modern digital engine monitors normally will capture data from a bunch of sensors, typically 20 or 30 different sensors. They'll capture this information between 10 and 60 times a minute. The older ones tend to capture data every 6 seconds or so. The newer ones capture it every second or even more often than that. So if you multiply the number of flights times the number of sensors times the data acquisition rate, which is quite quick, we've captured tens of thousands of data samples involving dozens of parameters. So back of the envelope calculation indicates that we probably have 200 billion data points in our database. It's a little hard to even imagine that. It's all stored on in the cloud on an Amazon server, all encrypted, so it's safe. But that's a lot of data, and as this database has grown, we have started to spend more of our time and energies thinking about what sort of interesting things we can do with this data, what sort of data mining we can do, how we can use this accumulation of real life data on general aviation flights that's never been available before. This is the first time that anybody's ever tried to pull this kind of data together in interesting ways that would be helpful to aircraft owners and helpful to the industry in general. And the fellow who actually has been spending most of the time on this is a close friend and colleague of mine named Chris Rather. Very interesting guy. He's a Bonanza owner. He's an A&P mechanic. He holds a PhD in operations research, and he absolutely loves getting involved in research problems like this. So when I mentioned to Chris, we were talking, we usually have Sunday brunch together, and when we were chatting, I was sort of talking about the old thing about we wind up flying into more headwinds than tailwinds. He said, well, why don't we crunch the numbers and see what we can find out? So he wound up analyzing 3,500 flights of late model Cessna 182S Skylanes. These are the restart Independence-built Skylanes that are powered by Lycoming IO-540s. And he picked this particular group of airplanes to study for two reasons. One is that they're relatively slow, and the slower the airplane, the more profound the effect of headwinds and tailwinds would be. But the other reason, probably the most important reasons, was that this entire group of airplanes are all equipped with Garmin G1000 engine monitoring systems that capture lots of information, but in particular capture the two parameters that we were really interested in looking at, which was true airspeed and ground speed. And by looking at the difference between true airspeed and ground speed, we can determine whether the airplane is flying into a headwind or flying with a tailwind, and how much the effect that headwind or tailwind is having on the ground speed of the flight. So he analyzed these. He wrote a little software to analyze these 3,500 flights of this particular cohort of aircraft, Cessna 182Ss. And here's a graph of the result of that analysis, and in which the dark blue line is ground speed, and the magenta, the cyan line, the light blue line, is true airspeed. And as you can see, over this 3,500 flights, the ground speed was indeed significantly less than the true airspeed, which means that those airplanes were, on average, flying into more headwinds than they were flying into tailwinds. And if you look at the median ground speed and the median true airspeed, the differential there is about 7.5 knots. which means that on balance in this group of 3,500 flights, the net penalty was 7.5 knots. Obviously, some flights had tailwinds, some flights had headwinds, but when you average it all together, the net effect was that on balance you were losing 7.5 knots due to this effect of headwinds being more prevalent than tailwinds. And that's a pretty big deal. That's a 5-knot penalty on the average. That essentially the deck is stacked against us by, at least in these particular airplanes, by about 5%. So we started talking about why that was, and I'd always assumed that the reason that we always seem to have more headwinds than tailwinds is because we spend more time in headwinds than we do in tailwinds, because when we're flying into a headwind, we're traveling more slowly, so the flight takes longer, and when we're flying with a tailwind, we move faster, so we finish the flight more quickly. So on balance, we would spend more time flying into headwinds than tailwinds. But Chris pointed out to me that that was not the reason for the discrepancy that he found, because the analysis he was doing was based on the average true airspeed and the average ground speed during each of those flights. It ignored the length of the flights. If he had been doing the analysis based on time-weighted averages, then the deck would have been stacked much more against the pilots. But he wasn't doing that. So my explanation turned out to be wrong. That was not what was accounting for the fact that on average these airplanes were suffering a 5% loss of ground speed due to the prevalence of headwinds. So we looked at it a little bit more closely, and Chris came up with an alternative explanation to explain what we were seeing in the data. When we talk about headwinds and tailwinds, we usually have sort of a mental image like this, that there's, that the wind can be coming from any direction around the 360 degrees, and if it's coming from a direction that's closer to the nose than the tail, we consider it a headwind. If it's coming from a direction that's closer to the tail than the nose, we consider it a tailwind. So we sort of think about the arc of where winds come from as being 280-degree arcs that look like this. The forward arc is the headwind arc, and the rear arc is the tailwind arc. But in fact, that is not an accurate picture. It's I think the one that we typically use subconsciously, but it isn't the correct picture. And the reason it isn't the correct picture is because if the wind is coming from any direction other than directly off the nose or directly off the tail, we have to crab in order to maintain our ground track. And when we crab, we are losing a certain amount of what would otherwise be ground speed towards crosswind correction. And so if you draw the headwind and tailwind arc accurately, where it takes into account the fact that we have to correct for crosswinds, the arcs look something more like this. This is a little bit exaggerated, but you get the idea that because of the crosswind correction, the headwind arc is more than 180 degrees, and the tailwind arc is less than 180 degrees. In other words, for a crosswind to be ground speed neutral, it actually has to be coming from a little bit behind us, enough to make up for the ground speed that we're losing because we're crabbing into the crosswind. And of course, the stronger the wind, relative to the true airspeed of the airplane, the greater this effect is, and the bigger the headwind arc is and the smaller the tailwind arc is. So if the wind is significant compared to our true airspeed, then the forward headwind arc is more than 180 degrees, and the tailwind arc is less than 180 degrees, causing headwinds to be more likely than tailwinds. And the stronger the wind is, or the slower the airplane is, the more pronounced this effect is. We actually repeated the study, but instead of using Skylanes, we used Cirrus SR-22s, which was a faster airplane. And sure enough, the net loss that we came up with was a good deal less than the 7.5 knots that we were seeing when we analyzed the Skylanes. So this confirms what we pilots have long suspected about the deck being stacked against us. It's not an all wives' tale. It's true. There's a good physical explanation for it. And the explanation is not just the business about we spend more time in headwinds than tailwinds, which is the way I always thought of it. But in fact, it has to do with the fact that that most winds are not direct headwinds or tailwinds. They have a crosswind component, and crabbing to correct for the crosswind component has the same effect as a headwind. The crosswind will slow us down unless it is coming from a little bit aft of a beam of the aircraft. So I thought that was sort of interesting study. Just kind of a fun thing, not anything that was really relevant to the sort of maintenance stuff we usually do. We've done a bunch of studies having to do with maintenance-related things, and I'll tell you about one of them. One of the things that we are always most interested in SavvyAnalysis is cylinder head temperature, because we're convinced that cylinder head temperature is a significant factor in terms of cylinder longevity, and maintaining good cylinder head temperature control is extremely important. So I was, again, mentioning, Chris, that I've long noticed that Lycoming engines seem to run hotter cylinder head temperatures than Continentals. And I wanted to see if he could crunch some data and see whether that my conjecture about that was true. So he crunched a bunch of numbers, this time from a very large cohort of several 100,000 flights involving both Lycoming and Continental engines. And the result of his analysis came up with the following histograms. The top one is showing the distribution of cylinder head temperatures from Continental engines. The bottom one shows the distribution from Lycoming engines. You can see, if you look at the left side, these histograms are based on the number of flights that fell into each cylinder head temperature bucket. And you can see that we analyzed quite a few more Continental flights than Lycoming flights, because we have a very large number of Continental-powered aircraft in our database, notably Cirrus aircraft and Cessnas and so on. But we also have a good number of Lycomings. We've got a lot of RVs in our database. But we were taking a cross-section of a very large sorted group of aircraft, some Continental-powered, some Lycoming-powered. And sure enough, what the data showed was pretty much what I had speculated, that Lycomings on balance seem to run about 20 degrees Fahrenheit higher CHTs than Continentals do. This is also reflected in the fact that Lycoming's CHT red lines are significantly higher than Continentals. Most Continental engines have a CHT red line of 460 degrees Fahrenheit, and Lycomings typically have a red line of 500 degrees Fahrenheit. So the Lycoming cylinders, for a lot of good engineering reasons, run higher cylinder head temperatures. But when I was looking at this study, there was one thing that caught my eye in the Lycoming data, and that was the fact that the Lycoming data had this funny little double peak on it. If you look at the Continental data, it had a nice smooth bell curve, which is kind of what you'd expect. But the Lycoming data had this funny double peak to it. And I was curious, why would that be? That seems a little strange. You'd expect the distribution to be a nice smooth curve. And so we looked into that a little further and drilled down. And we determined that the double peak was being caused by Lycoming IO-360s, of which we have quite a few in our database, because most of the RVs are powered with Lycoming IO-360s. And what we figured out was that Lycoming originally spec'd the ignition timing on the IO-360s to be at 25 degrees before top dead center, which is a very aggressive ignition timing, and results in a pretty high CHT. And then subsequently, Lycoming issued a service bulletin saying that as a result of having a lot of high cylinder head temperature issues with the IO-360, saying that they had decided to change the timing on the IO-360 to a much more conservative 20 degrees before top dead center, instead of the very, very aggressive 25 degrees. And of course, if you retard the mag timing by 5 degrees from 25 to 20, you're going to result, one of the results is going to be significantly lower cylinder head temperatures. By contrast, most normally aspirated Continental engines are timed at 22 degrees. So 20 degrees is very conservative. 25 degrees is very aggressive. But the service bulletin was only a service bulletin. It wasn't an airworthiness directive or anything. And some people complied with it, and some people didn't comply with it. And so what we now have in the fleet is sort of a hodgepodge mixture of some engines that are timed at 20 and some engines that are timed at 25. And the ones that are timed at 20 have lower CHTs, and the ones that are timed at 25 have higher CHTs. And that was the reason for this peculiar double peak that we were seeing in the data. So I found that kind of interesting. Moral of the story is, if you're flying an RV or something else with an IO-360 Lycoming, and you're having trouble with your cylinder head temperatures, check the mag timing, and if your engine is one of the many that are timed at 25, consider retarding the timing. If it's a certificated airplane, you have Lycoming's official blessing in the form of that service bulletin to retard the timing to 20 degrees. If you're flying an experimental, you can time it anything you want. So I would, maybe consider splitting the difference and maybe timing it at 22 or something and seeing how that works out. But if it's a certificated airplane, we can't just time it wherever we want. We have to have authorized data to do that. But there is authorized data for timing the IO-360, a certificated airplane, to either 25, which is what it was originally spec'd at, or 20, which is what Lycoming changed its mind and authorized by a service bulletin. So that was kind of interesting. Another thing that we that I had Chris take a look at, something that I'd been noticing over the years and wanted to see if we could confirm with empirical data, was the fact that I noticed that the piston airplanes that were designed in more recent times, things like the Cirruses and Columbias and Diamonds and so on, typically had much more even cylinder head temperature distribution than legacy airplanes like Bonanzas or 210s or Piper Saratogas or the Cessna 310 that I fly, which was basically designed in the 50s. And that basically the engineers that design airplanes in modern times had much better tools to use in designing the cooling systems, the bafflings and the cowlings and all of that kind of stuff, than the engineers that were doing it back in the 50s and 60s, where they had very crude tools to do it. But at any rate, my observation was that the newer vintage airplanes had much, much better cylinder head temperature control and much more even cylinder head temperature distribution than airplanes that were designed in earlier times, like the one I fly. And so Chris did some analysis where he compared a group of Cessna 210s, which is kind of a legacy airplane designed in the 50s, and Cirrus SR-22, which is a much more modern airplane that was designed in the late 90s, and came up with, again, the following distributions, which pretty much confirmed my empirical, or my suspicions, where the Cessna 210s had a very, very wide CHT spread between the hottest and coldest cylinders, whereas the Cirruses had a very, very tightly clustered CHT spread, where typically the hottest and coldest cylinders were only 20-25 degrees apart, compared to 70 or 80 degrees apart on a typical Cessna 210. An interesting thing that came out of that study was that Chris also analyzed the pattern of maldistribution of CHTs for the Cessna 210, and he came up with a result that looked like this. And if you look at this is looking at each of the different cylinders on the engine, and which cylinder was the hottest running cylinder. And as you can see, the cylinder number 5 is a major problem child in these airplanes, in the Cessna 210s. And that in general, the even numbered cylinders, the ones on the left side of the engine, are very, very rarely the hottest cylinders. The hottest cylinders are almost always in the right bank, and most commonly cylinder number 5. And that sort of indicates that this problem is a systemic design problem with the Cessna 210 cooling system, rather than just some sort of a random maintenance-related problem where airplanes have bad baffles or baffle seals or whatever. Because if it was a maintenance issue, then you would expect the results to be much more randomly distributed among the different cylinders. But they're not. It's clearly a problem with the odd-numbered cylinders, and most definitely a problem with cylinder number 5, which is the front right cylinder on the Cessna 210, and it sits right behind the oil cooler, and it happens to be in that configuration, it's a very difficult cylinder to get cooling air to, just because of the configuration of the engine. So that was kind of interesting. We've done a lot more studies that I'll be talking to you again. Be talking to you again about, or talk to you about next month. That's really quite cool, where we have been able to derive really actionable intelligence to help individual aircraft owners spot problems with their particular airplanes and take corrective action, as opposed to the stuff that I've talked to you about today, which is really studies of broad swaths of airplanes. But I'll be getting into a lot more detail about that in the next webinar next month. But let me just conclude by getting on my soapbox and preaching a little bit. My rough estimation is that today roughly 50% of the piston General Aviation fleet is equipped with a recording digital engine monitor capable of capturing this sort of data that we've been analyzing. And I'm convinced, you'll see more about this next month. But I'm absolutely convinced that the potential benefits of collecting and studying this data and using it to provide feedback to the aircraft owners and the manufacturers and so on is extremely valuable. The potential benefits are huge. But unfortunately, the vast majority of data that is captured by these systems never gets extracted for analysis and winds up in the proverbial bit bucket, lost forever, because most owners, they'll put these fancy engine monitor systems in their airplanes, or nowadays they typically come from the factory that way. But very few owners take the time to extract the data and upload it for analysis. And so the vast majority of data that is being collected never gets into our database. In fact, I'm astonished at how many aircraft owners I talk to. They'll call up with some kind of problem, and I'll say, well, could you dump your engine monitor data so we could take a look at it? And it turns out they've never done that. They don't know how to do that. It just never occurred to them that dumping engine monitor data was a good thing to do. And so my challenge is to try to convince aircraft owners that this is something that they should be doing on a regular basis, in the same way that they send oil samples off to laboratories for a spectrographic oil analysis, or they have their oil filters cut open and inspected for metal. They should be dumping their engine monitor data and sending it in for at least automated analysis, if nothing else. My hope is that the next generation of these engine monitors will have the capability of automatically phoning home as soon as the airplane's on the ground and the avionics can get an internet connection, and send their engine data over the internet, so it isn't lost, without any manual intervention by the pilot. And in fact, we're just starting a trial program working with Dynon with their SkyView system, which has Wi-Fi capability built in and so on, to try to do exactly that. That program will specifically be targeted at experimental aircraft, but we're hoping that if it works well, that we'll be able to persuade other engine monitor manufacturers like Garmin and so on to add that capability to their equipment, so that the data does reliably get captured and doesn't wind up just scrolling off the end of memory. So that's my hope for the future. But in the meantime, I need to try to convince aircraft owners that they really should be extracting the data that their engine monitors are capturing and not let it get lost. As I mentioned, next month I'll talk about how we're starting to use this data to provide actionable intelligence to aircraft owners, so that they can see how the various parameters affecting performance, efficiency, and longevity, and general health of their power plants compare with other with hundreds or thousands of other aircraft of the same type, so that they can kind of see where they are in the spectrum. And we've been doing a lot of work with that. I think it's kind of exciting stuff, and I'll be sharing that with you in the webinar in March. And Tim, that's all the prepared material I have for tonight, but we can open it up for some questions if you like.
Okay, Mike, we got some questions that have come in here. Let's kick off with Barry. He's asking, did the CHT data show a difference between suppliers of engine analyzers? He's thinking of the Cubcrafters study, where they found that JPI engine analyzers with grounded probes read CA 35 degrees Fahrenheit higher than EI analyzers with ungrounded probes.
Well, we didn't specifically study that because we typically don't have information in our database Well, no, that's not true. We actually do have information in our database about what kind of equipment was used. We haven't actually studied that. I am aware of the Cubcrafter study, that's actually a very interesting comment, and it's something that I think we would have the capability of doing some analysis on in our database, because we do have information in the database about what kind of engine monitor equipment each aircraft is using to capture its data. So, that's a really excellent idea. I'm sorry I didn't think of it myself, actually, but I'll talk to Chris about it and see if we can do a study like that and see whether the results that we come up with in analyzing our data agree with the findings of the Cubcrafter study, which I am aware of that study. Good idea.
Okay, and Roger wants to know if the meaningful CHTs are the peak data or the average data. He says that my peak data only lasts about 3 minutes on climb out.
Well, we normally analyze, when we're doing these analyses, we normally analyze two different things. We analyze the peak CHT during the flight, and we also analyze the peak CHT during the longest stable cruise segment of the flight. And it's really the cruise segment data that we give the most credence to, because longevity is probably not that adversely affected by a short-term CHT exceedance that occurs just for a short period of time during initial climb. But it is, we think it is quite profoundly affected by the steady state CHT that occurs throughout the flight, particularly during the cruise phase where everything is being held constant. So the software that we've written to do this analysis tries to analyze tries to find the longest steady state cruise segment by looking for the longest segment of the flight we can find where various parameters such as altitude and airspeed and stuff are relatively constant, and we designate that as being the longest cruise segment, and we take the peak CHT in the course of that cruise segment. If that's not too complicated an answer, that's what we do. If it gets any more complicated, I may have to get Chris to join me, because he's the guy who actually wrote the code to do this stuff.
Hey, John's wondering, is there assistance to uploading data from you, telling us how and where to send the data?
Well, the data is always uploaded online. You don't send it anywhere physically. And there's a document. Actually, if you go to the SavvyAviation.com website, and you go into the resources page, there's a document. There's a page there called How to Upload Engine Monitor Data, and it lists a whole bunch of different brands of engine monitors, and if you click on the one you have, it'll give you detailed instructions as to how to extract the data and so on. So yeah, we have information online for lots of different makes and models of engine monitors.
Okay, and then to just follow on with that, Jerry's wondering, he says, I have 9 years of data from my IO-360. Does your company offer a service to automatically review it with recommendations?
Well, there's a couple of different things that we do. When you upload the data, it first of all goes through some automated analysis that looks for various significant exceedances. It looks for, we have a software algorithm called FEVA, which is a failing exhaust valve analytics, where it's looking for patterns in the EGT data to suggest exhaust valve failures. So there's a certain amount of automated analysis that goes on as the data is uploaded to our system. Once the data is uploaded in our system, then you have the choice of either analyzing it yourself with all of the tools that we provide, and all of that is free, or you can subscribe to a service that we offer called SavvyAnalysis Pro, which is $129 a year for a single engine airplane, where you can request our team of analysts to look at your data and get their evaluation. They write up a 2-page report on their findings and so on. Now you obviously can't ask our analysts to review all of the data for 9 years. You'll need to tell them specifically what flights you want them to look at. The automated analysis that we do will be performed on every flight. The human analysis obviously will only be done on the specific flights where you request the analysis.
Okay. Tom's wondering, on trying to analyze my data, there appears to be a lot of randomness with every power change or mixture change. It seems that the sensors are just too sensitive, or is it all useful info?
Well, either I or one of our analysts would have to look at the data to be able to give you a good answer to that. We do see a fair amount of data that is uploaded that has a lot of noise on it, and that really has to do with the quality of the installation of the engine monitor, in particular grounding issues and so on. So if you're seeing a lot of random jitter on the stuff, that is very likely noise, and usually the noise can be eliminated by some attention to detail, both in terms of making sure that the system is properly grounded and there aren't ground loops, and also making sure that the leads that go to the various sensors are kept physically away from ignition leads and from high current electrical wiring, like the main B+ line from the alternator and so on, that can induce quite strong magnetic fields that can put noise in the data. The sensors, most of the sensors on these systems are thermocouple probes that generate just millivolt level data, and so the harness is very, very susceptible to picking up noise, and it's very important that it be routed carefully to stay away from sources of noise. So again, there's really two issues here. One is noise getting into the harness. The other issue can be that the system has problems in grounding that result in noise getting into the system because of noisy power.
Joseph is wondering, if you want to install an engine monitor in a certificated aircraft, are you limited to type of monitors?
Not generally. Most of the certificated, you are limited to a certificated monitor, but most of the engine monitors have STCs that have very, very broad AMLs, aircraft model lists, and most of the engine monitors can be installed in just about anything. We don't normally run into a problem as far as that's concerned. On the other hand, at the present time, you can't put a Dynon Skyview into a certificated airplane, although they're working on it. I know EAA has been very instrumental in trying to overcome that hurdle so that some of the really incredibly good experimental avionics will be able to be installable in certificated airplanes, and the FAA seems to be kind of going along with that.
And Mark's wondering, have any aircraft manufacturers expressed an interest in your data mining results? If so, do you think they would make any design changes based on those results?
At present, I think the answer to the question is no. We did have one inquiry from Cessna where they were trying to hunt down a problem and were interested in getting some data from us, but I think that evaporated before we ever actually gave them any data. I think there's a lot of information in this stuff that could be very useful to aircraft manufacturers, to the FAA and NTSB, and various other people who are stakeholders in aviation safety. I just think it's kind of new, and people aren't used to thinking about getting this. A lot of people don't even know that exists. That when I tell somebody that we've got 1.2 million flights of information in our database, they kind of are quite surprised to hear that, because it's never been done before. So I think in the future this data is going to wind up being put to lots of interesting uses, but it's very new, and we're spending a lot of time just sort of brainstorming on what sorts of things that we can do with this data that would be most useful and most helpful to the industry and to the aircraft owners.
Yeah. Well, about 6 or 8 years ago, the NTSB took a close look at experimental aircraft accidents and published a safety study from it, and made a series of recommendations to industry, FAA, EAA, and I seem to recall that one of those recommendations was, hey, find a way to take advantage of these electronic devices on experimental aircraft which monitor data, to do exactly what you're talking about, I think. So there's a little bit of a nudge there from NTSB a number of years ago, and that leads into John's comment. John says, how about chairing an industry-wide data collection / analysis group of manufacturers and engine monitor suppliers?
Well, again, I think that might happen in good time. In December of 2015, the FAA Engine and Propeller Directorate held a big General Aviation Engine Summit and invited key industry players and the key alphabet groups to spend 2 days at the Engine Propeller Directorate up in the Boston area, talking about piston engine issues. I was invited to participate in that meeting, and I spent an hour presenting to the group a much earlier version of the information that I shared with you tonight. There was a lot of interest in the room, but the FAA works. The wheels turn very, very slowly at the FAA, and it takes a long time and a lot of patience for things to happen. I did sense a good deal of interest on the part of the Engine Propeller Directorate folks, and we are supposed to have another summit sometime in the first quarter of this year that I expect to be attending. And but these are the sorts of things that take a long time, because the FAA is a huge bureaucracy, and things don't happen very fast.
Yeah.
And that may be more true now with the Trump administration, because he has sort of put a lockdown on a lot of these agencies, and we'll see what happens. I'll share, this is neither here nor there, one of my IAs sent me an email yesterday, which I thought was really funny. Donald Trump had said something about that he had made an executive order that says for every new regulation that his executive branch agencies issue, they're going to have to remove 2 previous regulations, and he said, "Does this mean that anytime the FAA issues an AD, they're going to have to cancel 2 other ADs?" Which I thought was pretty funny.
That is funny.
We'll see. We'll see what this all means in the fullness of time.
Hey, Ralph's
That's
wondering.
a nice thought.
Yeah. Well, I mean, some ADs are there for a good reason, so I don't know. I mean, that would be a difficult thing to do, I suppose. But
there are a few that are overkill too. So.
Oh, right on. Hey, Ralph is wondering, have you seen a fair amount of data showing shock cooling?
We haven't done a particular study on that, but I was one of these people who had, in years past, drunk the Kool-Aid and was very concerned about shock cooling and was, reducing manifold pressure 2 inches every 2 minutes to make sure I was babying the cylinders, and that all changed after I installed a good digital engine monitor and started watching what the actual cylinder cool down rates on my engines were, and I discovered, much to my surprise, that it was actually very, very difficult to shock cool a cylinder, and that for example, Lycoming has a recommendation that cool down rates not exceed 60 degrees Fahrenheit per minute. So in an abundance of caution, I set a cool down alarm on my engine monitor so that it would alarm if I exceeded 30 degrees Fahrenheit per minute. And I discovered that it was very hard to get the cylinders to cool down faster than 30 Fahrenheit per minute, and that this cool down alarm would typically only go off maybe once every 2 years, and only when I did something that was, really, really abusive, like, a real slam dunk descent or something like that. So I came to the conclusion, based on my own observation with my own engines and my own engine monitor, that this whole issue of shock cooling is very much overblown, and that it happens much, much less frequently than we had previously imagined. And so nowadays, I happily will yank off 5 inches of manifold pressure at a time and not think of anything of it. And I know that if I do start getting excessive cool down rates, my engine monitor is gonna set off an alarm, and it very, very, very seldom happens.
Very interesting. Ian and a couple other people are wondering, are you collecting data from other engines, other manufacturers such as Rotax, Jabiru, Franklin, UL Power?
We do have some, shall I say, boutique types of engines in our system, but without going in and doing a database query, I can't tell you precisely which engines other than the typical Lycoming, Continental, Franklin type engines that we are following. And one of the areas we're very interested in, and in fact I've been having a dialogue with somebody at Diamond Aircraft about this, is that we're presently all of our analysis is on spark ignition engines, but I personally believe that aviation diesels are kind of the future of piston general aviation, and I would like to get us into the business of analyzing data from diesels. And most of the diesel, and that's kind of a different ballgame, because most of the diesels are FADEC controlled, where it's not just like an engine monitor that you hang on the engine. The engine monitor is an integral part of what makes the engine run, because they're all computer controlled. And so the data streams that come out of those things are quite different than what we're used to. But I think it's an important area, one that I'm personally very interested in, and so we're going to be expending some effort to get our analysis platform to start working with some of these new diesel engines that are coming to market.
Very cool. Wiley's wondering, I have recently installed a data recorder. When I have extracted data, it appears I only have CHT and EGT. It appears the installer didn't include manifold pressure or fuel flow to be recorded. Is my data valuable without the inclusion of power/fuel flow? Must I get the data to be connected to the recorder?
Well, I guess I need to know a little bit more about the system he has. We have lots of aircraft that use our platform that have older engine monitors that record only EGTs and CHTs and nothing else. And yes, that information is quite valuable. No, it's not as useful as if more parameters were gathered. In particular, when we're doing human analysis of the data, if all we have to look at are CHTs and EGTs, then we have to make educated guesses as to what the pilot was doing with the engine controls. Whereas if the engine monitor is capturing air data information and manifold pressure and RPM and fuel flow and stuff, then we don't have to guess what the pilot was doing because we can see exactly what he was doing. So it's very helpful to have that additional data. But certainly, even if all you are capturing is EGT and CHT, the data is quite important. If the system has the capability of capturing the additional data, and if it was just some sort of an installation issue, then I think it would be worth having that rectified, because the more data, the more different data points you're capturing, the more valuable it is in terms of our ability to diagnose issues.
And Bob's wondering, has a comparison been done between tractor and pusher aircraft? And if so, is there any major differences?
No, we've not done an analysis of that. I don't know how many pusher aircraft we have in our system. I imagine we have some long easies and stuff, but I honestly don't know the answer to that. I don't know if we have a statistically significant population of pusher aircraft in our system to be able to do any kind of meaningful analysis.
Okay, let's see here. Oh, Barry's just wondering, he says, I have an EI analyzer and low CHTs. He's worrying if he is fooling himself.
Well, I don't know. As it was mentioned earlier, the Cub Crafters study did seem to indicate that the EI probes were under-reporting cylinder head temperature. And I'm personally not convinced it has anything to do with whether the probes are grounded or not. I think it really has to do with the fact that the EI probes don't reliably make good physical contact with the bottom of the cylinder head temperature well, and that in many cases they're measuring the air temperature in the well rather than being in physical contact with the aluminum casting. But I haven't personally done a study about that. I'm aware of the Cub Crafter study, and it's available online. But that's the only information I have on that subject.
Okay. Don's wondering, can you quantify the dollars saved from analyzing engine monitor data versus the cost of the devices?
Well, that's hard to do, but pretty much the first time an engine monitor allows you to pinpoint a diagnosis and avoid, for example, pulling a cylinder, which happens all the time, it just paid for itself pretty much. So, I think from an economic standpoint, these things are pretty much a no-brainer. Not so much because of operational things where they, let you lean more accurately and save fuel and that sort of thing, but because they allow you to diagnose problems much more accurately in a non-invasive way. And so, when you have an engine problem, instead of taking it to a mechanic and having him attack the airplane with tools, you download the data and analyze it. It's the difference between, having a CT scan and having exploratory surgery. And I'll take the CT scan any day.
Hey, Walt's wondering, for the 210 versus SR22 CHT spread comparison, were they both injected engines? And does
they're both the 210s are Continental IO-520s, and the Cirruses are Continental IO-550s. They're both injected engines. Yeah, the problem is not a fuel problem in the 210s. The problem is a cooling airflow problem.
Okay, and a couple questions here about electronic ignition. Richard's wondering, is it possible to time a Lycoming IO-360 with the unison laser ignition, which uses a modified slick magnetos to 20 degrees instead of 25 degrees?
I would have to pull up the manual because I haven't actually worked on a laser system, but I'm almost certain that yes, you can adjust the timing on those things. There are some electronic ignition systems where adjusting the timing is more difficult, but I think my recollection is that the laser system, which pretty much plugs into the engine in a way that simulates a normal magneto. As you mentioned, it's kind of a modified magneto that can revert to magneto mode in the case of a failure of the electronics, if I recall correctly. I think you adjust the timing on that system in the conventional way.
Okay, and Don's wondering, can you tell the effect of CHT temps from electronic ignition systems variable timing versus fixed magneto timing?
Well, I have very limited data on that. We've got some experience with the ElectroAir STC, which is an electronic ignition that replaces one of the two mags on certificated aircraft. And we've actually had some problems with that system with excessive cylinder head temperature, and we've been able to troubleshoot it to the ElectroAir system has a manifold pressure sensor on it that advances the timing at reduced manifold pressures. And we've had problems with that particular aspect of the system causing excessive cylinder head temperatures, and we know that that's the problem because if we take the aircraft that's experiencing the problem and we disconnect the manifold pressure sensor, the problem goes away. So we know it has that the elevated CHTs are being caused by excessively advanced timing caused by the ElectroAir system. The last time I saw that was quite some time ago. It's quite possible that ElectroAir has updated their firmware to correct that problem, so it may not be a problem anymore. But that's kind of the extent of my experience in addressing that particular question.
Rodrigo's wondering, have you thought of using machine learning to predict failures on top of your data?
Boy, have we ever, yes. In fact, Chris went through a machine learning course at Stanford University, specifically in anticipation of us doing that, and that's definitely in our plans.
Cool. Vince is wondering, do you analyze Prebuy engine data?
We do, absolutely. And I'll next month when I do the webinar, I'll be talking to you about something that we prepare called the SavvyAnalysis report card, and one of our hopes is that the report card, which is a graphical report based on automated analysis of historical engine monitor data, will ultimately turn into sort of a Carfax for airplanes, where when somebody, when you buy a pre-owned airplane, one of the things you always wonder about is how was the engine treated, and how likely is it to make TBO and all that kind of stuff. And we actually have the technology, I think, to provide a lot of information like that. And I think my hope is that, in the future, it will become something that buyers expect sellers to provide, to provide engine monitor data that will be analyzed so that the prospective buyer gets a report card on the engine that shows how it's been operated.
Okay, question here from...
This is really all very new stuff, and we're just starting to scratch the surface of it. So we're doing a lot of brainstorming, and I can tell, this the people in this seminar, their gears are turning, which is a good thing. But there's probably tons of stuff that we can do with this information that we haven't even thought about yet.
Mm-hmm. I've had a few questions come in about uploading data and that whole process, getting out of the aircraft and into some system to analyze it. So how is that typically done with the monitors that you see out there? Is there a little data card, or how does it actually work?
Well, it's a little complicated because it varies by engine monitor type, but there are basically three broad classes of equipment that we have to deal with. There is equipment such as like the Garmin G1000, which records its data on an SD memory card, and you plug an SD memory card into the unit and you go fly, and it records the data in real time on that SD memory card. If you don't plug an SD memory card into the G1000, then the data doesn't get recorded anywhere and it gets lost. So you normally always fly with an SD card in there. And then when you want to extract the data for analysis, you just remove the SD card from the Garmin, stick it in your laptop or some little computer that has an SD card reader, and upload it to the platform. So that's the simplest case. The second case, which is a pretty broad spectrum of engine monitors, are ones that record the data internally in internal memory, and then have a facility for you to transfer that data to a USB thumb drive. And so on those, when you want to extract the data, you plug a USB thumb drive into the monitor. It has a USB port. You plug a thumb drive in, and you typically power up the unit with some button push or something to tell the unit that you want to dump its accumulated data onto your thumb drive. And it goes ahead and does that. And then you pull the thumb drive out, and you take it home, stick it in your computer, and upload the data. The third case, which is the most clumsy case, it has to do with older generation engine monitors. And a good example of that is the JPI EDM 700, which is probably the single most populous engine monitor in the fleet, but it's quite an old technology in it. And it was developed back before there was USB and before there were SD cards, and so it was installed with a serial port connected to it. And the idea back in the 80s or whenever the JPI 700 came out was that you would bring your laptop computer down to your airplane, and you would hook your laptop serial port up to the unit, and then you'd run some software on your laptop, and the unit would transfer its data via the serial port to the laptop. And the problems with that are, first of all, almost no computers have serial ports anymore. Second of all, so you wind up, if you're going to do that, you wind up having to use some sort of a USB to serial adapter, and it winds up being kind of a mess of cables. Second of all, nobody really wants to be hauling their laptop down to their computer in order to do that, down to their airplane in order to do this. So JPI, because there are so many of these EDM 700s out there, JPI came up with two solutions to this problem, because it just started to become impractical to be dumping the data over a serial port into a laptop computer. One solution, which is what we generally recommend people do who have these units, is they have created a little $200 box that is powered by a 9-volt battery, I think, and you stick it in your glove compartment. And when you want to extract data from the unit, you pull this box out of your glove compartment, and it has a cable that plugs into the EDM 700 serial port, and it has a USB socket that you stick a thumb drive into, and it just totally automates the process of grabbing the serial data and writing it onto the SD card. So you don't have to use the laptop for that. It's very small, and it's intended to just be kept in the airplane so that it's there when you use it, when you need it. The other solution is that you can send your EDM 700 back to JPI factory, and they'll make a factory mod, and it will come back to you with a USB port on it instead of the old serial port. Effectively, they take the same logic that's in this $200 box, and they actually stick it inside the instrument. And I think the cost to modify the instrument is also about $200. So you can do that, and then the instrument has a USB port on it, and you can stick a thumb drive directly into it, and it will write to the thumb drive. So that pretty much covers all of the common cases that we deal with. It's either an SD card that plugs into the unit, or a thumb drive that plugs into the unit, or a thumb drive that plugs into a box that plugs into the unit. And I think that pretty much covers the variety of cases that we have to deal with. And again, my hope is that all of this stuff's kind of annoying, and my hope is that in the future we will have engine monitors that just get a Wi-Fi internet connection, transmit the data, and the pilot never has to mess with it.
Yeah, that sounds like it'd be the way to do it, the new industry standard. I suppose right now the USB port sounds like the most recent way that it's done most conveniently.
Well, I don't know. I actually prefer the SD card method that Garmin and some other manufacturers use, but either of them is acceptable.
Yeah,
but both but both of them require the pilot to actually do something, and my ideal would be to not have the pilot do something, because that would guarantee that all the data would get captured and none of it would get lost. That's really the objective.
Right. Well, I was wondering how much data, hours, number of flights, etc., is typically stored in the engine monitor systems.
It varies dramatically. The early units, like the EDM 700, had a pretty limited capacity. They would store maybe 20 or 30 hours of flight was all that they had capacity for, because back then memory was expensive. Now memory is almost free. The new systems can store very large amounts of data, and things like the G100 that use an SD card, it really is a function of how big an SD card you plug in, but they can record enormous amounts of data. So it really depends on the age of the unit. The older ones could record less before they had to be dumped. The new ones can record lots more.
Yeah. Bruce is wondering, what inhibits our use of Wi-Fi to connect aircraft to data centers and move past the quote-unquote sneaker net approach to moving data off the aircraft during flight?
Just the manufacturers being willing to do it. And as I said, we started a a pilot project with Dynon with the Skyview, just because the Skyview actually already has Wi-Fi built in as standard equipment, and so it seemed like an ideal platform to start. I mean, they built Wi-Fi in not for this purpose. They built it in really to provide an ability to update their databases in the unit. But Wi-Fi is Wi-Fi, and we said, well, hey, if you got Wi-Fi to update your databases, maybe you could use that same Wi-Fi and dump the engine monitor data out. And so we're working with them on it. I think that it's actually going to wind up being something like an iPhone or Android app that talks to the unit via Wi-Fi and then uses the owner's regular cellular data connection to transfer the data over the internet. The problem is, that most people, or well, I don't know if I can say most, but an awful lot of people don't have a Wi-Fi internet connection in their hangar. But everybody has a smartphone. So probably the most promising next incremental step would be to automate the movement of the data from the box to your phone, and then an app that knows how to transfer it from your phone, over the internet.
Mm-hmm. Thomas is wondering, regarding CHT differences between Lycoming and Continental, can engine design for sensor location or sensor type explain the temp differences between the two engine types?
Yeah, that's actually a significant part of it. It's interesting because yesterday I had about an hour and a half conversation with Rick Moffett, who for many, many, many years was the vice president engineering for Lycoming, and he's retired now. But we talked about the fact that the location that we measure CHT, which is normally the threaded CHT boss that's on the underside of the cylinder, is not even close to being the hottest part of the cylinder. The hottest part of the cylinder is typically very close to the top of the combustion chamber dome, but it's in a location where you just physically couldn't locate a sensor. And during test stand runs, when they're actually developing cylinders, they do drill lots of holes in the cylinder head and install thermocouples in there and make measurements there, but it's not the kind of thing that could be done with aircraft in the field. So there's a significant delta, and this is something I sort of had a vague sense for, but Rick had a lot more detailed information on it. There's a significant temperature delta between the really hottest part of the cylinder head and the place on the cylinder head where we place the probe to measure it. And that difference can be on the order of 100 to 150 degrees Fahrenheit. So if you're seeing an indicated CHT of 300 degrees, the hottest point on the cylinder head might really be 450. And so yes, the differential between what we see at the measurement point and what the really hottest point on the cylinder is quite significant.
That kind of feeds into Jay's question here. He says, I have a Mooney M20J with a Lycoming IO-360. The prior owner had hooked up an EDM 700, but the number 3 cylinder uses a spark plug gasket CHT probe. The factory bayonet probe is still in place for the primary CHT gauge. Naturally, the log data I upload shows the number 3 CHT is about 40 to 50 degrees cooler than the other cylinders. Is the factory CH probe always installed in this number 3 cylinder, and would that affect the accuracy of accumulated data?
There's a significant inaccuracy involved if you measure the CHT in different locations on different cylinders, and we see the situation that he's talking about quite a lot. But the proper way to do that, JPI makes what's called a piggyback probe that screws into the threaded well, and in turn has a threaded well on the back of it that the factory probe can screw into, so that both probes are measuring CHT at the same location. And so my recommendation for him would be to abandon that spark plug gasket probe and to purchase the JPI piggyback probe, which is it's probably $100. But then he'll be getting consistent readings between that cylinder and his other cylinders.
Okay, great. Well, let's wrap it up here, Mike. Boy, thank you so much. Interesting presentation. You're leading the industry in this area. Thank you so much for doing that. I mean, this, I can see nothing but providing long-term benefit to the whole industry. And being a leader like you are, I just want to give you a big thank you for doing that. I know you're doing it so we can all benefit from it. So much appreciated, sir. Please take a moment and share closing comments.
Well, I'm also doing it because it's fun.
You're a data
It's
geek.
really kind of cool. Yeah, that's right. I am. At any rate, I just wanted to quickly go over my upcoming webinars. As I mentioned several times, the March webinar, which is going to be on March 1st, will be a continuation of this one on big data, and we'll be talking about report cards, alerts, our failing exhaust valve analytics, some more of the really cool stuff that we're doing with this data, but specifically focused on stuff that where we're looking at not big swaths of airplanes like what we were talking about today, but looking at particular airplanes and providing feedback to the owners on how their particular airplane is doing, which is probably the use of this data that is most useful to owners. Some of this cohort analysis is probably useful to the industry and the safety community and so on, but what individual owners are most interested in is, well, how about my particular airplane? And so that's what I'm going to be focusing on in the March webinar. April, the title of the talk is "What Does Airworthy Mean?" And I'm going to be talking about an interesting, I guess, a dispute that I wound up being in the middle of arbitrating between a buyer and seller of an aircraft, and we'll sort of get into the whole question of what does it mean when you say an aircraft is airworthy, because that actually turns out to be a more complex subject than it looks like on the surface. And the June one is entitled "Buy or Walk Away," and it's kind of talking about when you buy an airplane, you have a pre-buy inspection, you discover that there are some things wrong with the airplane. How do you make a decision as to whether to go ahead and buy the airplane anyway, or to walk away from the deal and go seek another one? So that's what we're going to be talking about in June. And I'll close as usual with an invitation to sign up for my newsletter, monthly newsletter, if you haven't done so already. Where the newsletter typically contains pointers to maintenance-related articles, recorded webinars, upcoming webinars, all kinds of stuff like that, and also if you haven't already done so, you might want to check out my book on Amazon. If you Google Mike Busch Manifesto, it'll take you right to the book on Amazon. And if you're interested in maintenance, I think it's a book that would be of interest to you. And that's about it. Tim, until next month.
Mike. Yes, great. Thank you so much. I noticed that in May you didn't have a webinar written down there. Is there something going on? You have a conflict with May, or we just don't have that one identified?
No, did I screw up? Maybe I screwed up.
Went from April right to June.
I'm sorry. I did screw up. I guess that one should be May. We'll have to see what's the first Wednesday in May. I'm sorry, I messed up the slide.
Okay.
Glad you spotted
no
that.
Problem. So the June 7th will actually be the first Wednesday in May, and that's the buy or walk away.
Is it May 7th or May? I don't know what.
Whatever the first Wednesday in May is. Yeah.
Right. At any rate, the first Wednesday in May will be buy or walk away. I messed up. I apologize for that. I don't know how I managed to do that, but definitely I'm planning a May webinar.
Okay,
I may
that's
not.
May 3rd.
I'm not sure. I'm not sure I'm going to do. Usually, I don't. I either skip or reschedule my August webinar because I'm recuperating from AirVenture. But other than that, I don't plan to skip any.
Good to hear. Okay, May 3rd, write down on your calendar. May 3rd is buy or walk away.
May 3rd. Sorry about that.
Okay. Just wanted to check you on that. So wonderful. Well, thanks again, Mike, so much for spending time with us tonight. Great presentation. We had a lot of people say thank you so much. Great job. Interesting new stuff. So to everybody that tuned in, thank you so much for tuning in, and hope you can join us next week. Have a great night, everybody.
Yes, thank you, everybody. See you next month.